Hello friends, Namaskar. Welcome to CEC live lectures. So we have been discussing about the transmission media in the series of lectures, and in the previous series we had talked about the wireless or the unguided transmission media, in which we were talking about the radio waves. Now in today's lecture we are going to talk about another type of waves which is very important in digital communications. Those are known as microwaves. So we had seen that in the electromagnetic spectrum, radio waves, they are from 30 kilohertz to 1 gigahertz you have the radio waves, and then from 1 gigahertz to 300 gigahertz the waves are known as microwaves. So these waves have frequencies between 1 and 300 gigahertz. Now unlike the radio waves, these waves are unidirectional waves, right? So therefore what do we mean? That when an antenna is transmitting the microwave, they are narrowly focused. When we saw in the radio waves that when an antenna transmits, it's omnidirectional, but here it is unidirectional, so it's more focused basically. So when sending and receiving antennas, they have to be aligned, they have to be they have to be kept in face to face with each other, right? Of course being unidirectional has the obvious advantage, because we had seen that there was in radio waves there is a major problem of interference from any other antenna which could be on the path of the wave, right? But here because these are aligned, so there is no problem related to interference by another antenna, and so there is it's very clear that which two antennas are actually going to exchange the data. So microwave propagation is line of sight propagation. When we say line of sight, we mean that the sending antenna and the receiving antenna, they have to be in direct sight of each other, right? So the towers that are far apart also, they need to be very tall, so that they can communicate with each other directly. So the towers are generally, we see that the towers, they have got the antennas mounted on them because they need to be in direct sight. The curvature of the earth, as we've discussed earlier also in the propagation mode, and there are other blocking obstacles also, they do not allow two short towers to communicate by using microwave. So repeaters are also required in this case of microwave propagation, because if you want long distance communication, then repeaters need to be installed so that they can reinforce the signal, because as the signal will move, because of distortion, the signal and attenuation, the signal might get weakened. So therefore there are multiple differences if you see between radio wave and microwave. Radio wave basically it follows the curvature of the earth, or it's the ground propagation, whereas microwave is following the line of sight propagation. There it is omnidirectional antennas. Here we are talking about unidirectional antenna, which are going to be face to face with each other, right? There is no need for repeaters in radio waves, but here we need repeaters. Now because these are high frequency microwaves, they cannot penetrate the walls, right? So now this of course is a disadvantage, because if the receivers are inside buildings, then the microwave propagation will not work, unlike radio waves. So microwave band is relatively wide, because there are 299 gigahertz frequencies in this, from 1 gigahertz to 300 gigahertz. So therefore sub-bands, wider sub-bands can be assigned, and a high data rate is possible in use of microwave. So therefore of course this microwave also, you need permissions to use certain portions of this band, but certain portions of the frequencies of the microwave band of they can be used for communication purposes, and they do not require permission from any authority also. So when we are saying that unidirectional antennas are there, so basically there are two types of unidirectional antennas which are used for microwave communications. The first type of unidirectional antenna is known as the parabolic dish, and the second type of microwave communication antenna or unidirectional antenna is known as the horn. So this diagram it shows what a parabolic dish looks like and what a horn antenna looks like. So we can see that in a parabolic dish antenna, it is very much similar to the the dish TV antennas that we see on roofs of the houses, etc., for taking the signals of the cable TV network, etc. So it's very much similar to that. And what happens in this is that the waves which are moving parallel to each other, they get reflected, and they sort of conglomerate at a single point, which is known as the focus point, right. So here it is basically every line which is in symmetry or in the line of sight, it gets reflected at the curves of the dish, and they intersect and make the focus. So parabolic dish basically it works as a funnel, and it catches a wide range of waves and directs them to a common point, right. So in this way more of the signal is recovered than would be possible by a single point receiver, because the surface area of the disc is such that it captures all the waves and then it focuses on a single point. So outgoing transmissions are broadcast through a horn antenna, right. So which is aimed at the dish. Now the microwaves, they hit the dish, they are deflected outward in a reversal of the receipt path, right. Whereas the horn antenna, which we are using for mainly, which is being used for sending the signals, it is like it looks like a gigantic scoop basically. It's like a big spoon, you can say, and outgoing transmissions, they are broadcast up the stem, which is like the handle of the spoon, and they are deflected outwards in a series of narrow parallel beams by the curved head. So you have a narrow handle and then you have a curved head. So the signals they travel from the handle, they reach the curved head, and from there the signals are broadcast. And when the signals are received, they are collected by the curved surface or the scooped shape of the horn in a manner which is similar to the parabolic dish, and they are deflected down the stem. So they are then sent, so they collect, the signals are collected and then they are sent into the stem. So microwaves are used for unicast communication such as cellular telephone, satellite networks, and different types of wireless LAN. So microwave definitely is a successful communication technology or media for data communication. Then we have the third type of waves, which are known as the infrared waves. So we all know that infrared is the very common type of technology which is used in remote controls of different things, right. So we have television, or we have different types of remotes that we use. So those are using these infrared waves, and their frequencies are 300 gigahertz to 400 terahertz, right. So therefore these are very high frequency waves, and they can only be used for short range communication, right. So now because they are so high frequency, they cannot penetrate the wall. Now this is a very advantageous characteristic, because this prevents interference between one system and another. So if we can imagine that in the house, when we have got multiple remotes and we are using one remote, so the other device in the other room is not going to capture that kind of signal, because the wave is so high frequency that it cannot even cross the wall of the room, and therefore this creates an isolation, and it can help in creating better and smaller networks which are required within the local or within the small territories of the houses. So this characteristic also it makes these for useless for long range communication, because these waves they cannot move for longer distances. We all know that in our remote also it has got a very limited range up to which the signals can travel. After that the signals get weakened. And there is another thing that you cannot use the infrared signals outside in the open, because the sun also has infrared waves in its sunlight also has infrared waves, and therefore those infrared waves can also interfere with the communication. So these are a few limitations with the infrared signals, but definitely infrared waves are used for communication within the devices, right. So this is almost 400 terahertz. So there is excellent potential for data transmission, because it's very high bandwidth, very high range is there. So wide bandwidth is there, and it is used for digital data at a very high data rate. So there is an organization or an association called the Infrared Data Association, okay, which is for sponsoring the use of infrared waves, has established standards for using these signals for communication between devices. So, we know we use the wireless keyboards or we use the wireless mouse, there are printers, etc. So, to connect these devices using wireless mode, the IRDA has got its own standards which are being used extensively. So, now some manufacturers, like, they provide a special port called the IRDA port that allows a wireless keyboard to communicate with a PC, right. So, the standard originally defined a data rate of 75 kbps for a distance of up to 8 meter, but now the recent standards which are coming, they are giving data rates of up to 4 mbps, which is very high data rate. And infrared signals, they are defined by the IRDA, they transmit through line of sight. So, therefore, it is required that your keyboard and your computer, they have to be kept point to point, or the keyboard has to point, or the IRDA port has to point to the PC, otherwise transmission will not occur. Very similar to the case of remote control also, that the device and the remote have to be facing each other, otherwise the infrared communication will not work, because this is a direct one-to-one communication, this is a unidirectional communication which is happening. So, friends, this is a lot about the waves and the different types of waves which can be used to build wireless networks or to exchange the data. Now, we come to a very significant portion of computer networks which are built using the satellite network. So, satellite networks is one of the major and most important segment of networks which is making communication faster, seamless and more secure. So, if you talk about a satellite network, what is a satellite network? Basically, it is a combination of nodes. So, like in computer networks, we say that each device is called a node. So, here also we say that these are nodes, and some of these nodes, they could be satellites which provide communication from one point on the earth to another. So, a node in this network can be a satellite, it can be an earth station, it can be an end user terminal, or it can be a telephone. So, any of these things can be considered as a node in case of a satellite network. So, satellite networks, they are, although we can say that there are natural satellites also, such as the moon. So, why should we not use the natural satellite for relaying nodes in the network? So, and we always see that artificial satellites are preferred. So, there are two reasons for this, that it is not easy to install electronic equipment on the natural satellite, right. Whereas, if it is an artificial satellite, it is very easy to install electronic equipment to regenerate the signal that has lost its energy during travel. And also the natural satellites, they are at a much larger distance from the surface of the earth. So, therefore, you cannot use those satellites for communication purposes, because it will create a long delay in the communication. So, therefore, because of this reason natural satellites are not preferred, but artificial satellites are commonly used for building communication networks. So, satellite networks, they are also like cellular networks, and in this what happens is that the earth is divided into cells, okay, and the entire planet is divided into cells, okay, and satellites they can provide transmission capability to and from any location on the earth. So, no matter how remote the location is, the satellite can be used to reach that location. So, this is a major advantage of satellite communication, and that is why it is being used for high quality communication available to undeveloped parts of the world without requiring a huge investment in ground based infrastructure, because this is most accessible form of communication. Now, when we talk about satellites, there are some important terms and some important concepts which we must understand. So, first thing is the orbit. So, we all know that orbit is the path along which a satellite is going to travel around the earth, right. So, an artificial satellite will also need to have a path. Now, the orbit can be an equatorial orbit, it can be an inclined orbit, or it can be a polar orbit. So different types of orbits can be there, and we will see that different types of satellites use different types of orbits to take rounds around the earth. So the period of a satellite, there is basically the time required for the satellite to make a complete trip around the earth. So this calculation is given by Kepler's law, basically, which is used to define or calculate the period. And how do we calculate the period? So period is basically a function of the distance of the satellite from the center of the earth. So if we say that period, it can be defined by a simple formula which is given by the Kepler's law, that says period is equal to c into distance raised to the power 1.5. Now what is c? C is basically the constant, which is approximately 1 upon 100. So period that is calculated is in seconds, and the distance which is given is in kilometers. So we will try to calculate and see how you can find out the period, that is the total time a satellite will take to complete one round around the earth, one trip around the earth. So if you use the Kepler's law, then if you want to calculate the period of a satellite which is located at an orbit approximately 35,786 kilometers above the surface of the earth. So this is like a question, we will solve it and see. So the period will be c, c's value is 1 upon 100 into 35,786 plus 6,378. Now this 6,378 is the radius of the earth, because we are saying that the distance is actually the distance of the satellite from the center of the earth. So you have to calculate the radius and you have to add it to the distance. So it comes to around 86,579 seconds, which is equal to 24 hours. So what does this mean? This means that if a satellite is placed at a height of 35,786 kilometers above the earth, then it will take exactly 24 hours to complete one round around the earth, which is actually equal to the rotation of the earth, the time period for rotation of the earth on its own axis basically, right. So therefore, this satellite is going to be stationary to the earth, because it is rotating, it is moving at a speed which is same as the speed of rotation of the earth. So this type of satellite or this type of orbit basically is known as a geostationary orbit. So what is a geostationary orbit? It is that orbit in which when you place a satellite, the movement of the satellite will appear stationary to the earth. So this type of orbit we will call as geostationary orbit, and a satellite which is placed in a geostationary orbit is known as a geostationary satellite. So another important term which we need to see is called the footprint of a satellite. So we are saying that satellites, they also process microwaves and they have bidirectional antennas. So microwave and bidirectional antenna, we mean that it has to be in line of sight, right. So therefore the signal from a satellite is normally aimed at a specific area called the footprint, because no satellite can cover the entire surface of the earth. So there is a specific area which is going to receive and send signals to the particular satellite. This area is known as the footprint. Now the signal power at the center of the footprint will be maximum, of course, and as you move away from the center of the footprint, then the power of the signal will decrease. Now the boundary of the footprint is the location where the power level is at a predefined threshold. So if the signal goes below the threshold, this means that that region will not be a part of the footprint of that satellite. So the threshold value of the signal will decide what the footprint of a particular satellite is going to be. Now for the satellites also, we have different frequency bands for satellite communication also, because frequencies are reserved for satellite microwave communication, right. So these are again in gigahertz range, and each satellite will send and receive over two different bands. So we've already seen that microwave is, you know, a large band, and there are multiple, it's a you know, the bandwidth is quite wide there. So you can create multiple you know, bands out of it or sub bands out of it. So therefore every satellite will have one band for sending the signal and another band for receiving the signal. So the transmission from Earth to the satellite is called the uplink. That is, when the Earth is sending data to the satellite, it's called the uplink, and when the transmission is from the satellite to the Earth, it is known as downlink. So there are three categories of satellite which are, you know, based on the location of the orbit, or the satellites are divided in these categories, because we've seen that orbit is very critical, because orbit or the distance of the orbit from the Earth is going to, you know, determine the time period or the trip time the satellite is going to take. So there are three types of satellites that we look at. First is the geostationary Earth orbits, which are commonly known as GEO. Then we have the low Earth orbits, or LEO, and then there is another segment which is called the medium Earth orbit, or the MEO satellite. Now it's very important to see what is, you know, what satellites are known as the GEO, or they are known as the LEO or the MEO satellite. So if we look at this, you know, on there is a surface of the Earth, and closest to the surface of the Earth are the low Earth orbits, which are closest, you know, they are called LEOs. Then, you know, we can see that there are two Van Allen belts. Now Van Allen belt is actually a layer in the atmosphere which contains charged particles. So a satellite, you know, which is orbiting in one of these two belts would be totally destroyed, because, you know, there are energetic particles. So therefore the MEO orbits, they are not located in the Van Allen belt. So one set of, you know, Van Allen belt is there. Then you can, there is an area where you can place your MEO satellites, and then there is another Van Allen belt. So between the two Van Allen belts we place the MEO satellites, and then of course you have the highest satellites, which are known as the geostationary Earth satellites, which are of course at the distance of 35,786 kilometers, which is the geostationary orbit. So these are the GEO satellites. So GEO satellites are very critical satellites, but of course all satellites will use line of sight propagation. So line of sight propagation requires that, you know, sending and receiving antennas, they have to be locked onto each other's location at all times, so they cannot move. So therefore, you know, a satellite which moves faster or slower than the Earth's rotation will not be useful for short periods. Okay, you can only use it for short periods till the time, you know, there is a line of sight, or there is a, you know, they are in direct sight of each other, the sending and the receiving antenna. So therefore if you want that constant communication has to take place, then the satellite has to move with the same speed as the Earth is moving, right? So therefore the line of sight, or the, you know, the direct contact can only be maintained in that case. So such satellites are known as geostationary Earth satellites, because the orbital speed is based on distance from the planet. So only one orbit can be geostationary. This orbit occurs at the equatorial plane and is approximately 22,000 miles from the surface of the Earth. So therefore, you know, these are known as equatorial plane orbits also, because this is a fixed orbit only on which the satellite can be placed if it has to be a geostationary Earth satellite. So one geostationary satellite of course cannot cover the whole Earth. So one satellite in orbit has line of sight contact with a vast number of stations, but we all know that there is a curvature of Earth, and therefore much part of the planet will remain out of sight. So it takes minimum of 3 satellites which are equidistant from each other in geostationary Earth orbits to provide full global transmission. So actually you need 3 satellites which will, you know, so the footprints of all these 3 will cover the entire surface of the Earth. So therefore, you know, geostationary Earth orbits, or these are the satellites, you know, which are placed at that distance and they cover most part of the Earth. Then we have the MEO satellites, or the medium Earth orbit satellites, which, as we already discussed, they are placed between the 2 Van Allen belt. So, this satellite basically this takes 6 to 8 hours to circle the earth, right. So, and this MEO satellites basically they are used very critically in the GPS system. So, the global positioning system, it uses this kind of a structure in which 24 different satellites are placed around the surface of the earth, so that they can capture the location of the every point on the earth. So, this is very important for navigation system, the GPS system which is used in this case. Then of course, we have the last type of satellites which is known as the low earth orbit satellites. These have polar orbits and they are placed closest to the earth with 500 to 2000 kilometers, and their rotation speed is 90 to 120 minutes. So, they have a very high speed of rotation, and these are generally used for cellular type of access like cellular telephone system. Their footprint is also much bigger. So, these are close to the earth, their round trip time propagation delay is normally less than 2 milliseconds, which is acceptable for audio communication. So, therefore, LEO satellites are further they can be divided into little LEOs, big LEOs and broadband LEOs, but basically these are the satellites which are used for cellular communication. So, friends, this was all about the wireless transmission media. We shall be talking about other concepts related to computer networks in the following lectures. Till then, please keep watching CEC live lectures. Thank you so much.